I'll take the liberty of sharing screen and taking you across to the Teachers Academy. So before we start, I just thought I'll share this resource with you. This is the Teachers Academy blog where we will ultimately publish your papers in due course. I suggest there's a little conversation we had just the other yesterday, in fact. Let's talk about education. I think it may be a good idea for you people to even pick up some learning from the Friday evening sessions or Thursday, whatever you prefer. These sessions you don't do as a duty, you do because you as an individual have an aspiration to become better. And our goal is not because schools sign up or schools ask you. Our goal is because the happiness of teachers matter. So that's precisely why we are doing all the programs. So I suggest if you have time, oh please make time. We have a session on Friday at 5:30. I strongly recommend that. And in case you want to find out how music, art and poetry can better your teaching and learning, then we have a session on Thursday. It's called MAP, Music, Art and Poetry. These are brilliant sessions, absolutely unique content, original content. There is no AI made content because the coaches themselves come and host the sessions. They are beautiful. There's a nice reflection from Gyanshri School in the music, art, and poetry session on Thursday. Thank you for showing how music, literature, and art beautifully mirror one another. In music, soft notes like pianissimo and pauses create a mood of calm or reflection. Similarly, in poetry, soft sounds like or the use of ellipses slow down the pace and evoke quiet emotion. In painting, empty or negative spaces serve the same purpose, drawing the eye and creating a sense of stillness. All three forms evoke emotions. Wondering how deeply connected arts truly are. Even in dance, the measured footsteps, movements, eyes, and other facial expressions convey different emotions. So, this will give you an idea as to how good these sessions are. Similarly, there's a session yesterday, Education is a Transformation Journey. Let's embrace it. This is a little post by Manisha Khanna. This is a book reading session, by the way, on Friday, where we are reading My Good School. And we are trying to decode what really is education, learning, schools, and schooling. So that's all in that. Let's get down to productive failure. We are on the chapter and we were talking about direct instructions and discovery learning. Good evening. It's Saturday masterclass time, 5:30 p.m. I like calling Saturdays as learning forward Saturdays because this is where we hope to help you take your learning forward. Thank you all for coming here so meticulously and regularly. And even more, like the session we hosted this morning, which I need to mention. This morning, I had a conversation with the group of teachers who have joined the masterclass from Sunbeam School Lehartara. And I want to share this because I think it's relevant to everyone. And I'm going to request Lehartara School. It'll be wonderful if you could write a little post on what we talked this morning. And if you want, you can count that as one assignment. So, some highlights of that are that I suggested to them, as you people are finding it challenging to start or take a head start for what we call assignments, why not the schools do group assignments like you make group videos last year? And the whole idea of doing that was that you sit down and construct your thoughts, you collaborate, you become a team, you design, you collect data, and you deduce data. The whole idea about productive failure is whatever you do will have some learning. And I did speak to them this morning. It was nice. If any school would like a call like that, please ask Your teacher ambassador or one of you can ask me for a time and we would be happy to host a call to help you get started. I gave one example to them this morning, which I thought I should give right now to everyone. I said, okay, go to the basketball court. Next time a game starts in your school, I'm now trying to tell you how you can create a study or a case study to be precise. I said, look at the five basketball players, find the junior most one, find the most experienced one, list them out. Count how many times they cross the half line. Count how many times they succeed in scoring. Count how many times they fall back, and do this physically over a period of time and collect some data. So you can design something like that. And then from the data, try and see why some person could not score the baskets. Now, if they couldn't score the baskets, then what did they learn or contribute to the game? And you'll find out what is productive failure. So this is a very simple example I give. You could do this anything in your school on a campus, but please don't tell me or give me theory. What we read today applies to my class. I've done this with a child. No, you have to do data gathering. This is against your system of bringing up and learning in school. It's an antithesis of this is theoretical, this is practical. Theory apart, practicals apart. They don't connect. So that's our whole idea of designing learning like this is because you understand that while learning which you do, there always is a productive failure in every learning you do in your class. Something will always be positive for everyone in your productive failure. So try and find that. Manisha, may I start reading?
Yes, sir.
Thank you. Today on the panel, we have Manisha and Minakshi. Thank you, Minakshi and Manisha, for joining the panel today. We will continue with the chapter on discovery learning and direct instruction. So we will now think turning direct instruction on its head. This is what the whole story is about, and you want to challenge the direct instruction model you use in your current learning system. The answer lay in the direct instruction model itself. If one is going to turn the fundamental assumption on its head, then why not turn the model on its head too? When Copernicus questioned the fundamental assumption of, this is a difficult word for me, so forgive me if I spell it longly, Ptolemy's geocentric model, he generated the alternative model of turning the model on its head. So if you recollect from the last time, we talked about how they had the earth revolving and how the sun was the center instead of earth being at the center of the solar system. It wasn't accepted. Likewise, it actually changed the whole model of learning. So the fundamental assumption of the geocentric model, he generated the alternative model of turning the model on its head. That is, instead of earth being at the center of the solar system, he made the sun at the center. Likewise, in making learning easy does not necessarily ease learning. Then maybe the alternative model is to turn the direct instruction model on its head. As we saw earlier, direct instruction involves explicit instruction followed by problem solving. Learn first, solve later. It is a two-phase model, an instruction phase followed by a problem solving phase. We will see that in figure 2.3. The instruction phase provides clear, explicit instructions and demonstrations, immediate feedback and correction. The problem solving phase provides opportunities for learners to apply what they have learned by solving problems. And this sequence of instruction followed by problem solving or IPS instruction, problem solving acronym, can repeat as often as desired or necessary. Turning the model on its head would mean starting with problem solving followed by instruction or PSI1. We'll see that in figure 2.4. Solve first, learn later. That is it. Quite simple. The way to extract the value of failure in a problem was to follow it up with explicit instruction. After all, it is conceivable that the process of generating suboptimal or incorrect solution to the problem can be productive in preparing students to learn better from the subsequent instruction that follows. Thus, productive failure is not the same as discovery learning, for it combines the benefits of constrained discovery learning through problem solving followed by instruction. However, like intuition, being conceivable is not enough. Just because something is intuitive or conceivable does not mean it is true. I needed to turn the conceivable into demonstrable. So, look what he's saying. I needed to turn the conceivable into demonstrable. And this is what I'm trying to tell you. When you do a case study, you have to do something demonstrable. I needed an experiment. Go easy on doing your case study. Let's get the flow of a chapter or two and then jump into it and use a chapter to create your case study. That's the way you'll do it. A clean way to compare productive failure and direct instruction. An experiment that would demonstrate that engaging students in problem solving activities deliberately designed for them to fail could in fact help them learn better from subsequent instruction, and engaging them in direct instruction. So when we are talking about 2.1 figure, direct instruction means you have instruction, it's followed by problem solving. And productive failure means you just give the problem solving straight away and instructions come later. It's like preparing a DIY manual after you've done it. Setting up the experiment. The experimental logic itself is fairly simple. But designing a good experiment requires thorough planning and attention to detail. Now, this is what you have to do. This is how you'll design an experiment. So, your case study is actually an experiment which you are designing. You're not reporting everything that exists. AI can't do what I'm asking you to do. AI can't have five of you sitting together, applying your mind, looking at something in your school happening, and from that creating a design. Now, this is what AI can't do because AI is not there watching the school, that particular act, that particular thing happening in your school. It's not there. So, that's exactly what we want the teachers to work with. And as hard as it is to design a good experiment, it is sometimes even harder to recruit people to participate in the experiment, especially when the experiment is on something called proactive failure. Nobody wants to be a guinea pig, especially if it involves failing a lesson. I learned after I approached several schools and explained the experimental study I was planning to do, its underlying logic and hypothesis. So here we are. You are all becoming guinea pigs in our case study of productive failure. And all of you are having around tenterhooks. Where do we start? How do we start? And for the last 60 days, starting April, when we started this productive failure to almost now end of May, you're really having to think, where the hell has Mr. Dutt pushed us into? Well, let me tell you, I also didn't know where I would go with you. And that's where we are. Nobody bought it. Everyone wanted some evidence first, which was fair enough. But how was I supposed to get such evidence if no one gave me a chance in the first place? Besides, the mere presence of the word failure seemed to throw them off, and they would throw me out. Even with the qualification productive, they would focus their attention on failure. It was undesirable to position failure so overtly and explicitly in the foreground. Look at the cover of the book. It's so hard hitting. It's red. And it says productive failure. Productive going up, failure going down. It's a very aggressive design for a cover. But good things can happen on the other side of failure. I finally got the nod from one school whose principal decided to take a chance on me. It was pure luck. Amidst all the trying to stumble upon a school whose principal happened to be my high school math teacher. In the years since, she had gone on to become a school principal. I don't quite know why she took a chance on me, but I will always be grateful that she did. Hats off to Sunbeam School, who took a chance on me on helping design this reading of the book Productive Failure. I'm sure they also didn't know what they signed up for. And I'm so happy that there are over 50 of you who are now working towards a certificate program who will actually make an effort to create 5 experiments, 5 case studies. She assigned one of her math teachers to work with me. One school, one teacher, and her math students. The study was on. We could now begin designing the experiment proper, and there were a number of things to consider and design for. Giving chance a chance. Once I had a sample of students who agreed to participate in the experiment, I would randomly assign students into one of these two conditions: productive failure or direct instructions. Randomization is the key. Imagine picking teams for a game. If you handpick the best players of one team, that would not be fair. The same goes for scientific experiments. If we do not randomly assign participants to different conditions, like different teaching methods, we risk bias. Pre existing differences in abilities or knowledge or skills might affect the results. But the variable we are studying, sorry, not the variable we are studying. By giving chance a chance, random assessment ensures each participant has an equal chance of being in any condition, making the groups comparable. So if you look at your groups from various schools, it's a random assessment. When the groups were designed to attend the Sunbeam Masterclass, they all random. Likewise, when people who signed up for the webinar, it's purely random. That's even more random than the people who have been introduced through the GSA membership. It's like shuffling cards before dealing them. Ensuring a fair game where differences in outcomes can be attributed to the strategies used, not the initial deal. This way, randomization ensures that any differences in learning outcomes can be attributed to the teaching methods, not to the student's prior abilities or characteristics. All else being equal, next one was to control all variables except for the teaching method. Imagine you're trying to find out if a particular spice enhances the flavor of a dish. You would want to keep all the ingredients, cooking time, and techniques the same, changing only the amount of the spice. If you simultaneously alter other factors like adding a different ingredient or changing the cooking time, you cannot be sure if the change in taste is due to the spice or these other changes. Similarly, in scientific research, controlling variables means keeping all factors constant except the one we are studying, all else being equal. You change the one thing that you want to study the effect of. In my case, the teaching method. Therefore, I ensured that all students were from the same school, learning the same curriculum and the same concept and the same teacher for the same duration in a similar time of day and in a similar time of environment, and so on. In a lab experiment, these variables are easier to control. In an actual school or formal learning environment, it becomes hard. But one must try as best as possible. This is what we are urging you to do. Please attempt. Even if you can't attempt 5 studies, you can do one beautiful study in the next year. And believe you in me, this will change your life. The study you design, the case study you create. Let me tell you, we will, if all goes well, we'll try and do a book against what Dr. Kapur has written, and we'll ask him to write a chapter in it. So we can go that far if you produce some wonderful, what you call assignments, what we call case studies or experiments. Tuning it up. Equally important is for the two learning methods to be designed well. Imagine a Formula One race where two teams have developed innovative but vastly different designs for their cars. One team has focused on creating a more aerodynamic shape to reduce drag, while the other put their energy into developing a more powerful engine for greater speed. before they compete. However, it is essential that each team ensures their car works well with their respective design. Both designs need to be well tuned before comparing. If the aerodynamic car was not being properly wind tunnel tested or the powerful engine has not been finely tuned, it would be premature to compare them. The race would not accurately reflect the potential benefits of the different design strategies, but rather the effectiveness of the implementation and preparation. Similarly, when comparing two learning methods, both should be thoroughly developed and optimized within their respective design frameworks. Both should be conducive to learning. So you're really designing productive failure and ring fencing for any risk. That's how you will design a good productive failure experiment. Both should be conducive to learning. If one method has not been adequately prepared or tested, it is disadvantaged from the start. A number of iterations and piloting goes on in the lead up to an experiment just to make sure both methods are working well before we subject them to a comparison. Go back to last week. We did that example about two basketball scores, two different people. Yes, people with similar abilities, similar age groups, on same terra firma, on same basketball courts, the same school. So you can reflect back on last week's experiment, which we shared when we were trying to find out who was more consistent. Only then we truly determine which method is better, as the differences in outcome can be attributed to the effectiveness of the methods and not poor design. So please design what experiment you're going to do well. Spend 1 2 months on your design. Go that far. And I just said earlier today, maybe you would like to do it as a group from your school. So do it. Go ahead. There's just no reason why that should not be acceptable. A lot of scientists for best things happen in the world work as teams. It'll help you build team in your school. You will connect with teachers who have been randomly brought in to do the productive failure assignment with you. That's one. Second, if you so feel and you design an experiment that will run over a period of months, weeks, maybe you do one. So up to you. We are flexible. We are learning from you as much as you are. So this whole idea of 5 assignments, don't think that is the cardinal rule. Last year we asked for 11 when we did Masterclass season 1, and we ultimately accepted 75% submissions. But that was videos. It was easy to do. Now this is tougher and more challenging to do. So we brought down from 11 to 5, and we are willing to accept even one of the best quality in the country and as an example in the world, which I can submit to Dr. Kapur to see. That's the whole idea. And he's going to visit us. So you better be prepared for that to make a presentation when he comes here, capturing the signal. One can design a nice experiment, but if the measurement is not good, the whole thing falls apart. Measurement is like the heartbeat of any experiment, the compass that guides our exploration. Good measurement ensures we are not just collecting any data, but the right data, precise, accurate, and relevant. We need to capture the signal if there is one. That is, if there is an effect in favor of one condition or the other, the signal. Our measurement should be able to detect it. For example, a test that is either too easy or too hard would fail to detect any difference because both conditions will end up performing either well or poorly, respectively. The trick is to design tests and surveys that are good at picking up a signal when there is one. There is a whole body of science behind the development of measurement systems. Suffice it to say, a whole lot of work goes into designing instruments that provide valid and reliable assessment of students' knowledge and skills before, during, and after the experiment. It is like taking snapshots at different stages of a journey. You can observe where the students started, how they progressed, and where they ended up, providing a comprehensive picture of their learning journey. Before the experiment, we assess the student's pre-existing knowledge and incoming characteristics, example, gender, age, grade, and so on, to establish a baseline. During the experiment, we keep track of how students interact, what they produce, and survey their experience on a number of variables like engagement, interest, motivation, anxiety, and so on. After the experiment, we evaluate what they have learned using a variety of instruments designed to pick up the signal. When comparing productive failure with direct instructions, we are interested in three types of signals. Let's mark this: procedural knowledge, conceptual understanding, and transfer. These three signals largely map into the three problem areas of remembering, understanding, and transfer. The three signals: how, why, and apply. Procedural knowledge is like knowing the recipe of a dish. It's about knowing the steps to solve the math problem, the how. For example, if you're taught a specific method to solve a quadratic equation and you can apply the method correctly to solve such equation, that's good procedural knowledge. In science, it might be the method to conduct titration in a chemistry lab. In language, procedural knowledge might be understanding how to structure a 5 paragraph essay. I will add a snapshot of this page for you. As all of you don't have a book, you can keep taking screenshots if you people want. Another way out is there will be a video recording of this which will help you with all this content. So even if you haven't taken any screenshots, you can replay the video slowly and read. Conceptual understanding, on the other hand, is about understanding the why. Recall from the previous chapter that understanding requires seeing and encoding the critical features and the deep structure of the concept. It is the stuff that novices really struggle with. It is like understanding why certain ingredients in a recipe work well together. In math, it is about understanding why a certain method or formula works. Why do we carry the one in addition? Why does the Pythagorean theorem hold true? In science, it could be explaining why increasing the temperature can accelerate a chemical reaction. In language, it might involve comprehending why certain literary devices, such as metaphor or foreshadowing, are effective in conveying a story's theme. If you can demonstrate these abilities, you have good conceptual understanding. Finally, now transfer. Transfer is about taking something you have learned in one context and applying it to another, often a new context. It is like using a recipe you know to come up with a new dish. In math, if you can use your knowledge of addition to understand and solve multiplication problems, or apply your understanding of geometry to solve real world problems like calculating distances or areas, that is a successful transfer. In science, it could mean using the principles of physics to understand why a curveball or baseball behaves the way it does. In language, it could be about employing critical thinking skills learned in literature class to analyze and interpret current events or historical situations. As you can imagine, the how can be hard, but most people can learn that. Any learning method worth its salt should at least develop the how or procedural knowledge robustly. The why or the conceptual understanding is much harder. A good learning method ought to be able to develop not just the how but also the why. In doing so, it would address the problem we fail to understand. But the hardest of them all is transfer, the ability to apply your how and why in novel contexts, contexts that you have not encountered before, thereby requiring you to flexibly adapt and apply. I call this the apply signal. On the one hand, what is the point of learning anything if you cannot transfer it to new contexts and problems? On the other hand, and as you can guess, research suggests that transfer is needed indeed the hardest and consequently rare, and therefore is often called the holy grail of learning. When children can't understand you in a class, no matter how hard you try, you know what it is. A learning method that can develop robust procedural knowledge, deep conceptual understanding, and demonstrate transfer is worth its metaphoric weight in gold. With the experiment well designed, the teaching methods finely tuned, and the measurement set up to capture the key signals, it is time for the battle of the methods. Now we're going to battle the methods. So there are two methods we are focusing on this chapter: productive failure and direct instruction. The battle: productive failure versus direct instruction. As the operational level, comparing productive failure with direct instruction, be it in a lab or in a classroom, essentially boils down to figure 2.5. We'll see that soon. When learning a new math concept, should learners be first taught the concept and then solve problems? That is direct instructions. Or solving problems that lead to failure first and then be taught the concept? That is productive failure. After running several studies for a range of topics, example ratio, statistics, many others, in a number of schools, what we find: direct instruction, first give instructions and then do problem solving. IPS, productive failure, problem solving, and instruction. So PSI. Compare productive failure versus direct instruction. That's what we are doing here. Show the both methods need a high level of procedural knowledge about the target concept. This is the how signal, the kind of knowledge that gets tested on standardized tests, facts, procedures, and some basic problem solving. However, if you look at the second set of bars in figure 2.6, you can clearly see that productive failure students demonstrated significantly denoted by 3 stars, deeper conceptual understanding than direct instructions. This is why signal, which if you recall, had remained elusive when my teaching days. The same was also true for transfer and the apply signal. The third set of bars in figure 2.6, which we are coming to, show that productive failure students demonstrated significantly better transfer to novel problems. Although not salient, statistically speaking, the effect on transfer was much stronger than on conceptual understanding. And endangered both deep sorry, let me go back and get this word correct. Engendered both deep understanding and transfer, was therefore a stellar achievement. I call it the productive failure effect. Let's closely look at the graph. So we'll take a pause so that you can see it. It shades productive failure in darker color, direct instruction in lighter gray. So we're looking at learning outcomes, the how, the why, and the apply. So there are 3 columns, 3 bars. In procedural knowledge, the how, both are same. You have to explain the how. In conceptual understanding, that's where you see that productive failure gives more. And in transfer and apply, there you see productive failure gives more. So how could be common? The why, which means the working, you learn in productive failure. Your concepts become clearer. And what you as a teacher are trying to transfer becomes even better. A quick note: what we mean when we say something. A quick note about what we mean when we say that something is statistically significant. Statistical significance is simply a way to determine how probable it is to get the difference between the two methods purely by chance. If the chance of getting a difference between two methods purely by chance is high, then we cannot deem it significant because there is a high probability of getting the effect just by chance. So we can't go by probability and chance. It is what we might call a random effect. However, if the chance of getting the difference is small, then we can be more confident that it is not a random effect, that one method is indeed better than the other. How small is small? Enough depends on the domain. In my domain, the learning sciences, anything less than 5% is deemed significant. That is, if there is less than 5% or 1 in 20 chance that the effect could be random, it is considered significant. we give it 1 star. If there is less than 1% or 1 in 100 chance and the effect could be random, then we give it 2 stars. And if there is less than 0.1% or 1000, we give it 3 stars. The effects on conceptual understanding and transfer are both 3-star effects. In other words, there is less than 1 in 1000 chance that the productive failure is merely a random effect. I then investigated how much was learning from productive failure versus direct instruction. Once again, statistics gave us a way of benchmarking how strong the size of the effect is. Think of effect size as the oomph of our experiment. It tells us not just a productive failure was more effective, that is what the statistical test does, but precisely how much more. If one thing to say Amy was faster than Ben, this is what we learned last time in the race, it is another to say she was a full minute faster. Now, if the race lasted an average 10 minutes, then it is 10% effect. But if the race lasted an average 100 minutes, it is only 1% effect. Quantifying the effect gives us a sense of practical significance of the finding. If a new diet improves health outcomes by 1%, you're not likely to switch. But if it changes health outcomes by 10% or more, you would at least think about it. Likewise, a teacher may not want to change her teaching method if the new method makes only a difference of 1%. But if a new method makes a 10% or 20% or perhaps 50% difference, then the teacher is more likely to pay attention to it and potentially switch to the new method. Furthermore, it is important to not rely on just one of the 5 studies comparing productive failure with direct instructions. Because a small sample of studies may not be able to produce a stable and robust signal of effect. One may also be accused of bias if one relies only on one their work alone. What one needs to look at a large number of studies in other labs in other contexts and domains carried out independently. So this is what we are trying to do. So all the groups from various schools are in different labs. They will create studies from different labs, and we will see how you use productive failure to further your learning, to take your learning forward. After all, science thrives on independent replication and extensions. And the gold standard technique for extracting the pattern of effects across a large number of studies is called a meta-analysis. So we carried out a meta-analysis of more than 50 studies in Sinha and Kapur 2021, reporting more than 160 experimental comparison of students in 4 different continents and counting. Our meta-analysis shows that the relative effect of learning from productive failure was up to 3 times. That's 300% that of learning from a good teacher for 1 year. Another way to benchmark the relative effect is in terms of schooling years. It seemed as if productive failure students were performing up to 2 academic years ahead of direct instructions. What we have here is not an incremental effect, but a breakthrough that is practically highly significant. And because more than 80% of the studies in the above meta-analysis were independent replication, that is, I or my students were not involved in them, it lends them even more credence to the breakthrough findings. Let's go one step further. What would be even more credible if there was an independent analysis in which I was not involved at all? Luckily, there are several, but most notably in 2023. In an even more comprehensive review of the literature by Zhang et al. 2023, et al. Means a group, by 13 eminent scholars after leading universities in the world led by Ton De Jong, largely demolished the case for direct instructions and concluded that the most effective method of deep learning is something that combines inquiry and direct instructions. Productive failure does precisely that. Inquiry and instructions come after that. So the basic knowledge fallacy. Another way to interpret these findings is we have 2 groups of students. Let's see how this happens now. who appear strikingly similar and highly proficient in procedural knowledge, the how, the basic or fundamental knowledge or foundational knowledge, but appear different in conceptual understanding, the why, and transfer to adapt and apply in novel context. Oftentimes, people argue that the foundation is extremely important and that everyone should have a strong foundation. So far, so good. But then they argue that higher order thinking, like deep understanding and transfer, could be developed after we have built a strong foundation. So let us build the basic efficiently as we can. This is usually through direct instructions, and we can worry about the deep understanding and transfer later on. This is a fallacy. This is what we do every day. I call it the basic knowledge fallacy. What my results show is how one learns the foundational knowledge influences how well they understand it and can transfer it. The learning path matters. Two different ways of learning the same basics can result in significantly different understandings and transfer. Learning is path dependent. This is important. Learning is path dependent. If we do not pay attention to how we are learning the basics, then we might be shooting ourselves in the foot. The damage to developing deep understanding and transfer capabilities might already be done, and a lot more work is needed downstream. If we do not fix the upstream problem of learning, the basics in a way that builds understanding and transfer, like in productive failure. So let's look at the creative fallacy. Remember group one? They were a group of children who were first shown how to play with a new toy. That's where we started the book. And then asked to play as they liked. Intriguingly, even though they had the correct knowledge of how to play with the toy as well as the freedom to play as they liked, they still weren't as inventive as group 2 children in their free play. Group 2 was more than three times as inventive as Group 1, if all would recall. We saw that. Well, a similar pattern unfolded with direct instruction students. They were given the correct knowledge of the concept and then asked to solve the problem targeting that concept. This is the challenge you face in the current education system. You will give them the knowledge, but they can't apply the knowledge. In my experiments, the same problem that was given to productive failure students to start with given to direct instruction students after they would learn the correct knowledge. And with the same instructions to invent as many ways of solving the problem. So I would compare the creativity with which they invented solutions to the problem. To be clear, we are comparing the creativity with which productive failure students solve the problem before learning and required concept with that of direct instruction students who solve the same problem but after learning the required concepts. Whereas all direct students, instruction students, were typically able to solve the problem correctly because they had just learned the concept. None of the productive failure students ever produced the correct solution. Understandably, of course, as they had not learned the required concept yet. However, the diversity and creativity of ideas, solutions, and representations produced by productive failure students was far greater than that of direct instruction students, who largely stuck to the correct taught ways of solving the problem. When we notice that they are sticking to the correct solutions mostly, we prompted them again to think outside the box and invent other ways. In spite of the prompting, they found it hard to go outside the box, so to speak. What was striking to me here is that correct knowledge, when given too early, seemed to constrain the development of inventiveness and creativity, much like it did for Group 1 students. We are used to thinking of knowledge as a file on a computer. It does not matter how you get that file. If you have it, you can use it as you like it. The reality is that knowledge can be a double edged sword when it comes to creativity. While knowledge in a domain facilitates action and work in the domain, it can also constrain from thinking outside the domain. Think about this. Whether you're playing with new toys or learning a new concept, more and more research is suggesting that how you learn the new toy or concept, the learning path or the teaching method, actually influences how creative and inventive you can be with it. Creativity is path dependent too. In this way, the creative fallacy is a corollary of the basic knowledge fallacy. So when you give knowledge, you already know that this is where you have to go. So you're actually killing creativity by that. The challenge for us is not to shun knowledge, but to marry it with experiences that harness and develop curiosity and open mindedness. And one way to do it is to design such experiences when learning new things, to situate and support the learning of the new things in creative and inventive and explorative problem solving practices. After all, the goal is not just to know more, but it is also think differently. And sometimes thinking differently requires delaying knowing a little. And that is precisely what productive failure does in a nutshell. Instead of starting with direct instruction on the targeted concepts, productive failure engages students to generate multiple ideas, solutions, and strategies for solving novel problems that target concepts they have not learned yet. It is important to understand that these are not just any hard problems. These problems, which we have seen, are carefully designed in a principled way. To admit multiple solutions, activate students' formal as well as intuitive knowledge and ways of thinking. Induce failure in problem solving to make students aware of the limits of their own knowledge and increase the motivation for the situational interest in learning the correct solution. In a curated and safe way, productive failure engages students. This is important. Sorry. In a curated and safe way, productive failure engages students in the creative design process of divergent exploration and invention, reinvention, refinement, while persisting through struggles and failure in problem solving. And it is precisely this failure that prepares them for learning from subsequent consolidation of knowledge, assembly orchestrated by the teacher as an expert. In a nutshell, fail first, learn later. So we are done with the comparison of direct instructions and productive failure. I shall take a screenshot of the key takeaways and give them to you. Maybe this is your pause point, and maybe you want to try this as an experiment. Convert direct instruction and productive failure comparison into an experiment. That's a thought. So look at the takeaways. One, direct instruction trumps pure discovery learning, but does not make direct instruction the most optimal method. Try and prove that. Second, productive failure designs for the bootstrapping failure of learning. Even though students fail at problem solving, targeting concepts they have not learned yet, the failure is designed to prepare them to learn from subsequent instructions. I'll pause here. A mountaineer sometimes takes years to attempt the same peak, trying it every season in the short span you get in summer to climb in the high Himalayas, and he learns. So every time, it's not necessary he'll make it to the summit. But from his attempts, he comes back with learning, and that's how he becomes more experienced. Unlike today, you have an agency, you have a guide, he tells you go by this route, wear these clothes, on this day be here, and you reach the summit. Now that's direct instructions. Go back to Hillary and Tenzing's time. That was productive failure. So productive failure trumps direct instruction. Robust evidence shows productive failure produces significantly better understanding and transfer outcomes than direct instructions. Making learning easy does not necessarily ease learning. I wish the people who are saying, let's simplify the curriculum, let's reduce this, would ever read this book. It would change the way they think. There is a time for failing and a time for telling. Thank you. My 45-minute session for today is, I guess, well done. We will do here, which is called part two, the science of failure. Let me create a bookmark for this. I will share this bookmark as well as a screenshot of what we have taken and give you some thoughts in the WhatsApp group. So look at that. Thank you all for joining us today. Thank you, Manisha and Minakshi, for being my panelists. In the attendees, I have large number of people, and there was a question this morning: are we going to stop the master class for summer holidays? No, we have promised 52 master classes throughout the year, and holiday is your time to read. It's up to you. We will go on. We will read every week. Choice is yours. So there's no chutti from a master class. This master class is your personal space. It's your connection with yourself. It's not a school duty. It's at 5:30 p.m. in the evening. And we hope you people will join us and continue reading with us throughout the summer break. Our reading will not stop. So Rajani has a comment. Let me see. Sir, I am just done with my experiment and excited to share the assignment. It's just a matter of compiling. Beautiful. Thank you so much, Rajani, for making that progress. Does anyone want to talk? I can happily help you unmute. You can just put your hand up and we can help you talk. That's very easy to do for us. Anyone? I'm taking a breath. I'll have a shot of water. Yeah, I have a panelist who's got a hand up.
Well, so should I speak?
Yeah, sure, Meenakshi, welcome.
We were talking about productive failure, but today I mean, this is not for productive failure, but just a thought that came to me while I was teaching my children. One of the things that we do nowadays is we have videos for everything. You know, everything is visual. Okay. And the end result that I feel has happened because of that, people are unable to imagine anything.
Yeah,
Place visually in front of them, they're unable to imagine it, right? Now, because children often say, we don't know anything, we have never seen this, nobody told us that. Okay, and we were also young at one point of time and we did not have these problems. We could imagine, we could visualize the DNA as well, and this and that. I mean, we did not see those. So I just wondered, are we going wrong in every sphere where we are teaching by making things too easy for our students? Productive failure is also another thing where we don't should not make things too easy for them, right? We let them fail and learn.
brilliant. I gave you the example of climbing a mountain, Meenakshi. And
Yeah.
that's I paused and gave that, and it connects with my life and mountaineering also. There were some treks we just kept doing again and again, and we did make it ultimately. So that's how you
Mm.
learn. And like you so beautifully said, you learn much more if you do it that way. So, on that note, thank you so much. I hope each of you has something to take away from here. And I love you all for the time you take out, the effort you take, part voluntary, that is on your part. So, if you look at your coming here, direct instruction from your school, go to the master class. And your decide to come here and not take anything back is productive failure. So, think about it. Thank you everyone for the patience you show and enjoy yourself. We'll just keep reading. Don't bother. It's not a question of holiday or not. Life is a holiday. You've come here on a holiday. Make the most of it. When you sleep, there'll be no doubt between life and holiday. So we are here on a holiday. Don't think your summer holiday is something exceptional. So let's enjoy the holiday together. Read and love what you do. That's most important. Manisha, anything you want to add? As you are the co-host with me.
The last part I really loved it. Life is a holiday and we need to make the maximum of it. And maximum we'll be able to do only when we'll be reading it. Reading, introspecting, and then writing reflection will be what exactly is the need of the hour.
Yeah.
So to enjoy a holiday, reading, yes, I am there. And as long I'll be there for the reading sessions. Thank you, sir.
Thank you. Bye bye. Love you all. God bless you.